Very good evening from India and very good morning as per Pacific time and in USA. So, I am Avinash Shirode, President of National Space Society, Nashik, India chapter. And we are celebrating this World Space Week from 4th October to 10th October. And every day we have very eminent speakers in the field of space technology. So today we have a very eminent speaker, Dr. Pascal Lee. Before we start, for the kind attention of the viewers, let us follow certain etiquettes while watching the live program. Please be in a quiet room or disturbance-free location. Please turn off your camera, that's video stop, to save the bandwidth. Remain muted, otherwise the background noise will be heard by all attendees. And the most important thing is use chat window to ask your questions in Zoom and comment sections in YouTube. Be respectful of the speakers and other attendees. Please note that this program is being streamed live on NSS Nashik India Chapter 2020 YouTube channel. I'm not going to take all these things today. Only thing is there will be introduction of the speaker, presentation by the speaker, then speaker discussion and question and answers, and I will be giving you tomorrow's program. So let me directly come to the program agenda. Today, our eminent speaker is Dr. Pascal Lee, who is a senior planetary scientist, is the chairman of Mars Institute. He is also director of NASA Houghton Mars project. And subject of his presentation is a very, very important humans to Mars. Let me introduce Pascal. Pascal Lee is the chairman of the Mars Institute, planetary scientist at the SETI Institute, and director of the NASA Houghton Mars Project, HMP, at NASA Ames. He holds a Master of Engineering in Geology and Geophysics from the University of Paris and a PhD in Astronomy and Space Sciences from Cornell. Lee's research focuses on water and caves on the Moon and Mars, the origin of Mars moons, and the future human exploration of the Moon and Mars. He has led over 30 expeditions to the Arctic and Antarctica for analog studies, including a 402-day winter over in Antarctica. I'm afraid he was not frozen. He is a recipient of the United States Antarctic Service Medal. Lee also works on surface systems for future Moon and Mars exploration, including drones, hoppers, rovers, spacesuits, and habitats. He was scientist pilot for NASA's first field test of the ACV concept pressurized rover. He also led the Northwest Passage Drive expedition, a record-setting vehicular traverse on sea ice along the fabled Northwest Passage and the subject of the award-winning documentary film Passage to Mars in 2016. Lee currently leads the HMP's Astronaut Smart Globe project and JPL's Globetrotter Planetary Hopper concept study. Lee is also interested in SETI. He argues that there are likely very few advanced civilizations per galaxy and that we might be the only one in our galaxy at this time. Lee's first book, he is also a writer, Mission Mars, won the 215th prize for excellence in children's science books from the AAAS. In his free time, Pascal likes to be walked by his dog Apollo, fly and paint. I'm afraid he really gets time for all these things. He is an FAA helicopter commercial pilot and certified flight instructor and an artist member of the International Association of Astronomical Artists. With this introduction, which is a very, very, very brief introduction, considering his career graph and research graph, uh, it could take pages and pages, but what we are more waiting for is presentation. So, Pascal, most welcome to our World Specific program, and now over to you.
Thank you, Mr. Shirode. I'm very honored and privileged to be your guest today, and I want to salute what you are doing for the National Space Society, which is really important. You have a role not just as a member of a U.S. organization, but a global role here in advancing space exploration, and I just want to commend your work on behalf of everybody here at the National Space Society. Today I have an exciting opportunity, which is to reach an audience in India, of course, but also globally. I've let a few friends know around the world that I'll be giving this talk, and so it's a really nice, exciting opportunity to be able to live at a time when our planet and everybody on it is sort of living as a small community, and so without further ado, I'm going to jump over to my presentation. So tell me if you see this. How is this? Okay, good. So it's looking good. So today I'm going to talk to you about humans to Mars. As Mr. Shirode indicated, I'm affiliated with three organizations: the SETI Institute, the Mars Institute, and NASA. But a lot of what I'll be sharing today are sort of my opinion, and so all these organizations should relax and are not implicated by what I'm saying today to all of you. Okay, but of course I'm very grateful for their support in what I do. Let me see here. So what is a human mission to Mars? And the way my talk is structured, we will talk about what a human mission to Mars is, why do we even want to go to Mars? Then we'll talk about how we will go to Mars. And then finally, perhaps the most important question, who will go to Mars? And this is a particularly exciting question, I think, because many of you who are listening today might be young adults or students still working in your sort of becoming aerospace engineers, and you might actually have an opportunity not only to, of course, see a human mission to Mars happen, but be part of it in one way or another, either from the ground or as a crew member. So pay attention is all I can say. And remember where you heard these things. So what is a human mission to Mars? That's the first question you have to ask yourself as an engineer. What exactly are we trying to do here? What is the challenge? And so to figure out how to do this. So Mars, of course, is first of all, the closest planet to us. If we were an extraterrestrial civilization entering the solar system for the first time, we would not pay attention to Mars. We would go probably straight to the Earth, which is the happening place from the standpoint of life. But we ourselves are on Earth, and we are looking out to the heavens. And so Mars is the closest opportunity for us with Venus, to go and look for life. Now, Venus, of course, is closer to the sun than we are. As you know, the temperature on Venus is very forbidding. The temperature on Venus is around 465 degrees Celsius. It doesn't even matter whether you're at the poles or the equator. It's relatively uniform. That's the temperature inside a pizza oven if you eat pizza. And the atmospheric pressure is crushing. The surface pressure is 90 bars, so 90 times the Earth's atmospheric pressure. That's what you have in the ocean at a depth of 900 meters, which is, of course, considerable. And it's not a good place to send people, in spite of prospects for possibly finding signs of life in the atmosphere of Venus, which, of course, is still in question. The atmosphere itself is also compositionally unfriendly to us. It's made of CO2. We cannot breathe that. And we have sulfuric acid rain, concentrated sulfuric acid rain at mid altitudes in the atmosphere. So that is also very, very nasty. Therefore, our eyes are turned towards Mars, because Mars, of course, does not have big open bodies of water today, but it is merely cold, and cold, we can protect ourselves from that. And therefore, it's a more inviting place and more manageable than Venus. Okay, next slide. So in terms of size, here is the Earth on the left, of course, with India at night on the far left, compared to the actual size of the moon, compared to the Earth. So the moon, to the surprise of many people, perhaps, is actually quite a bit smaller than the Earth. And because of that, gravity on the moon is 6 times less than what it is on the Earth. It's 17% of our Earth's gravity. Mars, I chose a picture here of a global picture of Mars, one of the most recent global pictures of Mars taken near Mars, which is an image of Mars by India's Mars orbiter mission, the Mangalyaan mission. And I love this picture. It's really beautiful. You can see the North Polar Cap and a number of albedo features that are very familiar and classical on Mars. But the point here is Mars is intermediate in size between the Earth and the moon. And sure enough, gravity is intermediate. It's 38% of the Earth's gravity. So let's say you weigh, I don't know, 100 pounds or 50 kilos. Okay. Well, first of all, consider yourself lucky. But second, you would feel that you weigh only 38 pounds, okay, or approximately 19 kilos, okay, on Mars. So this would be your felt weight. Now, in terms of distance, the challenge is considerable. At the top, we see the Earth-Moon distance. It's about 400,000 kilometers. You can travel from the Earth to the Moon in about 3 days. You can therefore do a round trip within a week. You can leave the Earth on a Monday morning. You arrive at the Moon Wednesday night. You can spend Thursday on the Moon, come back anytime. Let's say you catch a flight back to the Earth Friday morning. You are back home Sunday night. Monday morning, you're back to work. So you can do a round trip to the Moon in a week. And I think that we are likely to see space tourism to the Moon becoming something of an activity, especially in the next few decades here. Mars is a much bigger challenge. At the bottom, you see the Earth going around the sun. Of course, that takes 1 year by definition. And Mars is orbiting, of course, beyond the Earth's orbit. Mars travels around the it travels around the sun in 687 Earth days. So it's, of course, by Kepler's laws, it not only has more ground to travel by doing a wider orbit, but it travels more slowly. And so every now and then the Earth is passing Mars. When we are closest to Mars, Mars is on the opposite side from the sun for us. And when we're closest to Mars, we are at opposition. And Mars is therefore, the distance can drop to about 55 million kilometers, which is what it is pretty much now. So Mars is, we're very close to opposition at this time. And then at other times, of course, the Earth is on the other side of the sun from Mars. And then the distance becomes 400 million kilometers or so. And what's remarkable about that is that that's about 1,000 times the Earth-Moon distance. Okay, so going to Mars is not just the next step. It's really another giant leap beyond going to just to the moon. Now, there are different ways to go to Mars, and on the left you see what are known as conjunction, probably the way you want to explore Mars in the more distant future, because it takes about just 6 months to get to Mars, and then you have the benefit of being able to stay on Mars for a very long time. In fact, you have to wait for the Earth and Mars to reposition themselves to fly back to the Earth economically. And so typically you spend 18 months on Mars, and then it's another 6 months to fly back. So altogether, you're gone 6 months plus 18 months plus 6 months. That's 30 months. That's about 900 days. That's a typical conjunction class mission. So the good news with the conjunction class mission is that you spend a maximum amount of time on Mars, and the transit time is a relatively small part of your journey. In total, you spend 1 year in deep space, 6 months out, 6 months back. An opposition class mission is less productive in that sense, but it has the benefit of having a total mission duration that is much shorter. So you leave the Earth, you catch up with Mars, and there you spend anywhere from no time with just a flyby to about 40 days, which is about a month and a half. That's pretty much as you can do. And then you dive back into the inner solar system. You even do a Venus flyby. Venus may or may not be there. You just cross the orbit of Venus. We don't really necessarily care about Venus, although we can use Venus as a gravity assist. And then we catch up with the Earth. So in this scenario, you spend 300 days outbound, 300 days inbound, so in interplanetary space, and you spend very little time at Mars, okay? So this might be a good way for cargo delivery, for example, if you have a cycler going back and forth, okay? But it's not very productive if you have a human mission, because now you're spending out of 600 days, out of a 661-day mission, you spend over 600 days just in deep interplanetary space. However, this might be the way to go for early missions to Mars. The challenge that we face with Mars is the reliability of spacecraft systems, and so we want to have a total duration of our mission to be as minimal as possible, I think, for the early missions. So I anticipate that when we go to Mars first, we will use opposition class missions, and then eventually we will transition to conjunction class missions. In case you are at a cocktail reception and you want to come across as sort of knowing what you're talking about, and you run into an astronaut who's going to Mars, you can ask them if they're traveling conjunction class or opposition class. Okay. Now, where do we stand in terms of our space flight experience so far? So the longest single space flight ever, the record is still held by Dr. Valery Polyakov. He's a physician from the former Soviet Union. He flew on Mir, and the total duration of his flight was 437 days, 18 hours. So 1.2 years spent on a single space flight in a station. The longest total time spent by a human being in space, it's a record held by Gennady Padalka, and he has spent 879 days so far, so 2.4 years over the course of 5 missions in space. Park of the duration of a mission to Mars, okay, 600 to 900 days. Now, in terms of the US, the longest single space flight record is held by Scott Kelly, 340 days, and the longest time spent by a US astronaut in space in total is actually a record held by a woman, Peggy Whitson, and she has spent a total of 1.8 years, 666 days over the course of 3 missions in space. Now, we are also, of course, starting to do some simulations to get ready for Mars. The Russians, for example, hosted this experiment, which was conducted with ESA as well, European Space Agency, where 5 or 6 astronauts were locked up essentially for 520 days in this facility in Moscow. And they had different modules simulating different parts or different aspects of a mission. There was the transfer to Mars, and then once at some point they were landed on Mars and could go outside on EVA into a little sand yard. The conclusion of these studies, of course, is always very limited, but essentially, I guess the answer is if you can survive 500 days in a facility in Moscow, you are ready for Mars. Okay. Now, the truth is there's a big challenge to go to Mars. There are good things for you, and then there are bad things. On the left, I've listed a few good things about going to Mars. The day on Mars is 24 hours and 37 minutes. So that is very close to our day on Earth. I don't know about you, but I could use 37 minutes more each day to get everything done. Water, there's plenty of water on Mars. It's mostly frozen, and most of it is in the ground. But there's plenty of water on Mars. There's water in the polar caps. There's water in the atmosphere. The atmosphere of Mars is actually super saturated in water. So it contains pretty much as much water or even a little more than it can at all times. And then gravity is lower than on the Earth, but it's not too foreign. It's not too alien for us. We think that 0.38 gravity is closer to having gravity than not. In terms of our physiology, but that's an open question still. But there are a few bad things that are really bad, and I've listed for you on the right, from top to bottom, a list of 5 things that will kill you in chronological order of cause of death if you venture outside on Mars unprotected by a spacesuit or habitat. The first thing that will kill you within seconds is a very low atmospheric pressure. The atmospheric pressure on Mars is about 10 millibars, and so you will essentially die of violent decompression if you just walked outside unprotected. Science fiction movies that show that you can survive several seconds exposed to the Martian low pressure are incorrect. If you were exposed suddenly to 10 millibars, the gases that are dissolved in your bloodstream, the nitrogen and the oxygen that you've breathed in your blood vessels, in your veins, in your arteries, would expand, and you would die a cruel and unusual death within seconds. Okay, but let's say if that didn't kill you, then the next thing that would kill you would be the fact that the atmospheric composition of Mars is toxic for you. It's made of CO2. We cannot breathe CO2, so we would die of hypoxia, lack of oxygen, even if it was supplied at the adequate pressure within minutes. Okay, we would be brain dead within minutes. The third thing that would kill you would be the frigid temperatures. The average temperature on Mars is minus 63 degrees Celsius, okay, minus 80 Fahrenheit, and that would kill you within a matter of hours. So if you were, standing naked on the surface of Mars, which I do not recommend, you would essentially be frozen to the bone by the end of the day at those temperatures. And so, it's not even relevant to speak of frostbite. You would essentially be dead. Now, let's say that did not kill you within hours, then the dust will. The dust on Mars, we now know, has 3 issues with it. One is that it is toxic in composition. It contains things like perchlorates and peroxides in concentrations that are significant, of order 0.5 weight percent. That's actually substantial. It accounts for why the surface of Mars is so red. It's essentially rusted by these superoxides. Beyond the composition, there's also the particle size, which is extremely fine-grained. At least part of it is. And then the third issue is the particles likely to be very abrasive. They are made mostly of volcanic glass, volcanic material that has been blown around a little bit by winds, but are probably still pretty uneroded and therefore shard-like, a bit like the lunar regolith. Okay, and so for these three reasons, inhaling dust is a real issue. We do not want to be exposed to the Martian dust directly ourselves. And for science fiction movies that, for example, show an astronaut scooping up large amounts of Martian dirt to bring it into your habitat to grow potatoes, for example, okay, are not really realistic, because you would die essentially of exposure to the dust, and that would probably kill you over the course of a few weeks. The perchlorates in particular, okay, will attack your thyroid and cause you to essentially die, over time. Now, let's say that did not kill you, then you have radiation. Radiation on Mars is pretty strong. We think that it will probably induce cancer and will increase your chances of developing cancer and result in eventually death if you are exposed to it for months at a time, for many long months. Okay. Now, interestingly, when we talk about going to Mars, everybody is so worried about the radiation. That actually is probably the last factor that will kill you. In fact, you're likely to go on a 2.5-year mission to Mars without dying, and then you might die of cancer. You might have a greater risk of cancer of order 5 to 10% more than the average population after you come back to the Earth. But the reason why I think it's so prominent as a threat in people's minds is because there's very little we can do about it. Okay, shielding is difficult to achieve unless you bury yourself, and that can be done not by going really into a tunnel, which is not very realistic, but to just create sandbags and bury your habitats under sandbags, and sand on Mars. So that would be the solution. All these other problems, however, are a lot more immediate and would kill you. I mean, your chances of dying at launch are far greater than your chances of dying of radiation over the course of a Mars mission. So just to start with the launch, I think we have to really put radiation worry in its proper place, which is not at the top of our concerns for Mars. So why would we even go? Well, there's of course the fame and glory that people who would go to Mars would achieve. This is the return of the Apollo 11 astronauts. You can see riding on the back of the car in the front row, Neil Armstrong on the right, waving, Michael Collins and Buzz Aldrin. They will in the history books forever. And those who will go to Mars will also be in the history books forever. And so it's an attractive thing. Sorry, am I still on? Am I still on?
Yeah, now I can see you. Yeah, there was some
Okay.
technical problem at your end. Yeah.
Okay, possibly.
Please continue.
So let me go back to the slide.
Yeah.
Do you see the
please,
slide?
Please.
Okay. So this is on the left, what's known as a tree of life on Earth. Think of it as the family tree of all life forms on Earth. What's remarkable about this tree is that it's based on shared genetic information.
Pascal, share your screen.
Share my screen. It was sharing, but I have to do that again. Stand by. Okay. Is the sheet, do you see it? Yes? Yes? Okay. So what you see on the left is the tree of life on Earth. It's, I'll think of it as our family tree for life on Earth. What's remarkable is that what puts us on this same tree, all of us life forms on Earth, is a shared genetic material. And for those of you who are biologists, this tree is based on the sharing of 16S RNA. Okay, so well, 16S ribosomic RNA, and it's but think of it as just your DNA, and we're all connected to other forms of life on Earth because we have some DNA in common, and the more DNA we share, the closer we are to each other on this tree. But all of us, with no exception here on Earth, are related, and the most obvious interpretation of this commonality in genetics is that we all have evolved out of a common ancestor, a microbe, probably a microscopic organism that no longer exists in the fossil record because it's so ancient here on Earth. But we all essentially sprang out and evolved out of that, diversified and evolved out of that original common ancestor. Now, there is no life form on Earth that does not plot onto the tree, okay, that we are aware of. And again, this is really a definition of the tree of life on Earth. What we're looking for on Mars is the possibility of the first example of an alien form of life. What we want to find is a form of life on Mars that does not belong to this tree, that would not fit onto it, that uses somehow genetic material that is completely different, or something that we might not even describe as genetic material. But in any case, that is what we're looking for. And what is very important to understand then is that in order to determine that something that we find on Mars is alien, we have to find it alive. It has to be still alive or dead for a very short time, meaning a few days to a few hours, so that we could still do genetics on its genetic material. In other words, we could still determine its what its proteins are made of, whatever it uses for its chemistry. And so therefore, there's no amount of fossil searching on Mars that can establish that something that we see as a fossil on Mars is alien. We know that Mars and Earth are not separated completely, that we have meteorites that have come from Mars naturally. There must be Earth rocks on Mars right now as well. Okay, these rocks get exchanged because the Earth or Mars gets hit by asteroids and comets, and big impacts will eject rocks from the target planet to the other planet. Okay, and so there must be Earth rocks on Mars right now, as there are Mars rocks here on Earth, and therefore life could have been shared between the two planets. Life could have started on the Earth and seeded Mars, or life could have started on Mars and seeded the Earth. We could all be Martians. The point, though, is that even if we found life on Mars, it's not necessarily alien life. It could be just life that is shared between the Earth and Mars. And so to really understand whether or not life is a phenomenon that is more common in the universe, we really want to find an example of life that's completely alien and therefore does not belong to this tree of life on the left. And so therefore we have to go to places where we might still have a chance find living life on Mars today. Okay. So that's my favorite reason for going to Mars, is because that's a complicated thing to look for, and we need humans to do that. One way to search for life is to realize that all life on Earth needs liquid water. There's no exception. Even when you live in a desert, you have to have at some point some liquid water to survive. And on Earth, everywhere where there is liquid water that is clean, there's life in it. Okay? I mean, there's even life in water that is not clean, but it cannot be too toxic, because otherwise at some point you don't have life in that liquid anymore. Now, the good news is that there is a long history of there being water on Mars, liquid water. And on early Mars, we see terrain that has been carved by ancient rivers or valley. These are called valley networks, and they might not be rivers of the class in the classical sense. We can see that later. In the middle history of Mars, there are outflow channels, which are events in which large amounts of water seems to have come out of the ground. And then in recent times, there are these gullies that must have been formed also by the flow of some liquid, and it's most likely liquid water. Some gullies could be dry gullies, in other words, dust slides or sand slides. But in this case, that's not the case. These are clearly incised into the landscape, and they involve liquid water. And so it's a big surprise. We're not quite sure how these formed. Maybe by seasonal snow melt or periodic snow melt. Maybe by the seeping of brines, very salty water made of perchlorates as a salt, which allows the freezing temperature of water to be depressed from what it is normally 0 degrees C to all the way to a remarkable minus 70 degrees C for perchlorates. You all familiar with the fact that salty water, like seawater, does not freeze at 0 degrees C. The freezing point of salty water with sodium chloride, as in the common salt in sea, depresses the freezing point of water to about minus 4 or 5 degrees Celsius. Well, if you replace the sodium chloride by a salt that we know exists on Mars, the perchlorates, that will actually lower the freezing temperature of water to minus 70 degrees C. It's remarkable. So this is possibly what we're looking at here. These gullies could be formed by water that can still be liquid on Mars today at these very low temperatures because of salts in the water. But we don't know. In any case, Mars has a long geologic history, and I want to show this, not to go into details. You don't have to read any of this. Just look at the color bar at the top. There are 3 very early periods on Mars. Okay, the purple, the pre-Noachian, is sort of the planet itself forming and its crust, the big giant impacts like the Hellas Basin. All of this formed at the end of the pre-Noachian. Then we have the Noachian period, during which Mars may have had a lot more liquid water near its surface or at its surface than today. Mars, those are things that geologists are still arguing about. But there's no doubt that there was more liquid water near the surface of Mars at the time. I've suggested that it was under a very cold climate, not a warm climate, as many people assume. But again, that's a separate discussion. During the Hesperian, there was also episodes of water outpouring onto the surface, but more sparsely. And then, of course, the giant volcanoes were born at that time. Olympus Mons, etc., was born in the Hesperian, we think. But then, since about 3 billion years, okay, in other words, throughout the Amazonian, Mars has been pretty much the way it is today. Maybe, rusting over time, getting a little more degraded now, but a lot less has been happening on Mars in the Amazonian than very early on in its history. Okay, so it's truly a planet that was shaped very early in its history. And this is why it's so exciting to go look for what the origin of life might have looked like on Mars, because we think that this very early period during which Mars was warmer, at least the ground was, allowing liquid water to be more abundantly present near the surface. That was a time when the Earth was also experiencing the origin of life. And we think that this might have happened on Mars today and could have been preserved. So we are still interested in finding fossils on Mars that date back to the earliest times of the Noachian and early Hesperian. But in order to determine that it's alien, we still have to find it alive today. So we've landed in, at this point, 8 locations on Mars. The Viking Lander 1 site in 1976, sand, a few rocks. Viking Lander 2, rocks, sand. Mars Pathfinder and the Sojourner landing site. So Mars Pathfinder was a fixed lander, and it had a little ramp, in fact, 2 ramps. And it carried a skateboard-sized rover called Sojourner that you see here on the right. So what's interesting is that the mothership that took this panorama over time lost power because it was fixed. And so the solar panels got coated with dust, and at some point there was no longer enough power to relay data from the surface of Mars back to the Earth. But the rover itself, because it was moving around, was able to shake off the dust that was on its solar panels. And so the rover had no end of mission program into it, and it might still be going in circles around the lander, looking for a signal if its solar power panels are still working. Okay, if its batteries are not fried. But anyway, if you go to Mars and visit this site, keep an eye for Sojourner and maybe bring it back to us for display at the Smithsonian Museum. Okay, and then Spirit and Opportunity were the two Mars exploration rovers. Spirit landed at this location, which was believed to be a possible ancient lake bed. I think that's probably what this is. And then Opportunity went to a place where there were signs of hydrothermal deposits, minerals that were made at the time when there was both liquid water and warmth wetting these grounds. And sure enough, we found signatures of hydrothermal deposits at the Opportunity site. Then we had a fixed lander, Phoenix, that went to a very high latitude location, approximately 75 degrees north, where we expected to find ice as soon as we scratched the ground. And sure enough, we found ice, water ice, very near the surface. And then Curiosity, of course, is still going on right now with its nuclear power. Now, notice that smaller rovers can still use solar power, but once you get to a bigger rover, it's so massive that you can no longer power something like that with just solar panels. They would have to be too large. So we go with RTGs, radioisotopic thermal generators. In other words, nuclear power to keep these rovers warm, keep the electronics warm, and to power them, for long road trips. So Curiosity and the Perseverance rover that's on its way to Mars right now are both powered by RTGs. And then InSight is the latest thing that has successfully landed on Mars, which is a US fixed lander. And it's a geophysics mission with instruments contributed by Germany, France, and other partnering nations. So this is listening for earthquakes, trying to measure the amount of heat that is still being released from the interior of Mars, etc. It's a very good mission. Now, in all of these explorations and wandering, so far, no sign of life, no fossils have been detected, no sign of living life. The surface of Mars seems to be really dead. And in my view, since we have to find living life to do genetics on it in order to determine whether it's alien or not, we might as well start going to places where it actually has a chance of being found alive, which are places that could still be warm today. And a place that could still be warm today are the volcanoes of Mars. Here you have the four of the most famous giant volcanoes of Mars. There are others that are, Alba Patera is not shown, it's even bigger than Olympus Mons. Technically, it's not as tall, but it's actually a bigger volcano. And then there are other volcanoes on Mars that are not shown here too. But the point is, Mars's volcanoes might still be active. Some are so big that they must have been building up to their size over a large fraction of the history of Mars. And therefore, their chances of being dead now are actually not great. They could still be active. They're just not erupting. So, but they could still be active. They would be in what you call in a dormant state. They're not extinct. They are possibly dormant volcanoes. We don't know that for a fact. We have not detected any activity coming from the volcanoes so far, but that's the hope, that these volcanoes are so big they could still be active. And here is my favorite volcano, of course, Olympus Mons, the tallest mountain in the solar system. You can see at the bottom, I show you in profile Olympus Mons compared to Mount Everest. And I know Mount Everest is dear to you. Thank you for looking at Mount Everest for all of us in India. But here, Mount Everest is about 8.8 kilometers in sort of total altitude. Olympus Mons reaches 22 kilometers from its base to its caldera. Okay, so it's about 3 times taller than Mount Everest. One thing you might find interesting is that there's actually a reason why there's this factor of 3 difference between the tallest mountain on Mars and the tallest mountain on Earth, which is the fact that gravity is approximately 3 times less on Mars than on Earth. Mount Everest actually is pretty close to being as tall a mountain as the Earth can bear. In fact, throughout Earth's history, we can safely bet that there has never been a mountain that was significantly taller than Mount Everest. And that's because at altitudes that are equivalent to Mount Everest, the weight of the rocks making up Mount Everest starts to reach 2 limits. One is that the lithosphere of the Earth, the rigid part of the crust and upper mantle of the Earth, starts to bend downwards if you pile on more rocks, okay, on top. If you try to create a mountain on Earth that's taller than Mount Everest, it would actually sag. And then the other thing is that you're going to start reaching the crushing strength of rocks at the base of the mountain. Okay, so again, you create a bigger pile of rocks, and the rocks at the bottom are just not going to be able to stay, unbroken, and so they'll sort of spread out. On Mars, that limit is 3 times more tolerant, which is why Olympus Mons can build to the size that it has, but it can probably not grow much higher. And so therefore it's growing sort of sideways. The more lavas pour out near the summit of Olympus Mons, the more they sort of have to spread off to the sides, and eventually the volcano is sort of expanding in diameter, but not so much in height. Anyway, the flanks of these volcanoes are intriguing because we can see these lava tubes. In this case, they're collapsed. But imagine that some of these things are, well, first of all, they started as tunnels before they collapsed into valleys. And that some of these tunnels are still running across the sides of these volcanoes. And we even see in some places just a very small collapsed window above in the ceiling on one of these tunnels. So at the top here, where it says lava tubes, that's actually a skylight. In other words, a hole giving access presumably to a lava tube on a volcano on Mars. All right. What we're looking at is the Jeanne pit. It's about 150 meters in diameter. It is bottomless. We don't know how deep it is. We know that it is at least 150 to 170 meters deep. No matter how you stretch the imaging, we don't see any feature at the bottom of this pit. Okay, but we think that it's sort of in a similar situation as what's shown at the bottom, which is it's the skylight in the roof of a lava tube, which is a tunnel through which lava once flowed. Another way, of course, to reach the subsurface where it might be warmer than the surface of Mars is to drill. We don't have the technology to drill today, but I've been working on a project where we studied the possibility of using plasma drilling to reach a depth of 2 to 5 kilometers on Mars, where we might reach liquid water and therefore have a greater chance of finding living life there today. But that's still far on the horizon, but maybe you guys will see it. Those of you who are younger will see that in your lifetime. So why go to Mars in the end? I gave you my personal favorite reason, the scientific reason, but there's actually a long list of reasons that people have proposed. We go for science, for exploration, for the journey, for the adventure, for the human experience, I gave a talk not so long ago, this talk, not very long ago in Australia, and I actually offer $1 to any person who comes up with a reason that is not already on this list. I mean, it has to be a reasonable reason to go to Mars. And this person in Australia raised his hand and said, what about establish a new colony of prisoners and convicts? So if you know the history of Australia, you will probably smile at that. So I didn't quite, I tried to argue that I had already that listed in my list under store waste, but that didn't go very well. So I had to add, establish a new colony of prisoners and convicts, and awarded that person, with my $1 offer. But the point here is that all these reasons that are often given by people, like become a multi-planet species or human destiny, are unlikely to really shape uh, to move a nation to go to Mars or anywhere else in space. Okay, and that's because if you look at the history of exploration by any nation, this is true for China, for India, for the Greeks, for Europe. If you look at the history of exploration, we do not spend big amounts of money exploring to satisfy scientific curiosity. That is not why we do it. Okay, we explore because it serves the strategic interest of a nation. I often explain that James Cook was not sailing the South Pacific because the British Navy was interested in botany. Okay, they did botany, they did science on those missions opportunistically, but the core reason why James Cook was sent to the South Pacific 3 times is because uh, the French were also exploring the Pacific at the time, and it was very important for Britain to know the people in the South Pacific and to explore that region of the earth as well. So if you feel that you have a strategic interest to be met, that becomes why you fund expeditions of exploration, not because you're interested in the science. Even when we went to the moon, President Kennedy did not send Americans to the moon because all of a sudden in the 1960s we became interested in moon rocks. Okay, it's because we were in the U.S. In a race against the Soviet Union, and through the Soviet Union against communism, to reach the moon, to do something big in space that would allow the United States to show its leadership in space at the time. And so that was the reason why Apollo, of course, was funded and achieved. And of course, once you get to the moon, what else do? You're not going to open a law firm or a bank branch. You're going to do science. So science is what dominates your activity in these exploration endeavors, but it's not the reason why you go in the first place. This is why when people say, well, why do we send people to Mars and not robots? Because that's irrelevant. It's not a competition between performance of humans and robots that will make a difference between us sending humans or robots. We send humans at some point because we determine that it's in the strategic interest overall, not just for science, but overall for the nation to participate in space exploration with humans. That's why we send people into space, not for any specific scientific performance that would make humans superior to robots or not. Okay. So this is really important to understand. And we can even see this today in Antarctica. Nations go to Antarctica and have bases in Antarctica, okay, not because somehow Antarctic science is so exciting. Okay, I mean, Antarctic science is exciting, but the reason why nations commit large amounts of resources to establish a research station, a base, okay, at great cost, is because there's a strategic geopolitical advantage in being in Antarctica if you can. There are resources in the future maybe to be claimed. There are, there's some prestige to be gained as well by being able to run an Antarctic station in Antarctica. So all these reasons are part of the strategic motivation for going there. Now, once you are in Antarctica, what else are you going to do but science? And Antarctic science is very good, but it's not the reason why we're going to Antarctica and having expensive bases there. It's to meet the strategic interest. And so I think this is something that we have to really come to sort of accept and face and realize that's how people work. That's how humans operate. That's why we do things that are expensive, and there are important investments in our strategic interests. So I would argue that going to Mars is in the strategic interest of the nations who can be part of that effort. All right. This is a plot that I often show because the perception sometimes is that the Apollo program had two big benefits. One was that the United States beat the Soviet Union, so to speak, and showed that, the U.S. way of life was superior to communism. Okay, so that was one important demonstration or reason why we went to the moon that was achieved. And then the second reason is, of course, science. We got a lot of scientific knowledge from being able to go to the moon and bring back lunar samples. But the third reason that I think is actually the most important of them all, the main reason why it was advantageous for the United States to send people to the moon, is shown in this plot. Okay, what you have at the bottom are the years of last century, and on the y-axis, the number of graduate degrees awarded in U.S. universities. Okay, so that's masters and PhDs combined. And we're looking at 4 scientific fields: engineering, physics, earth sciences, and math and computer sciences. You can see that all 4 curves are trending exponentially towards the right. Okay, they're increasing exponentially towards the right. That, of course, the first order exponential increase is the growth of the population in the US. So the more people there are in the country, the more people go to college, the more people graduate, the more graduate degrees are awarded. But notice that there is a spike. There's a second order spike during the exact years of the Apollo program. Okay, in physics, in all fields actually, in math, in engineering, in physics. And that is because an entire generation of young people got so excited by the Apollo program that they went into these fields. Okay, and this spike doesn't look like much, but it's actually a doubling of what the trend would have been if you just smoothed it and got rid of that spike. Okay, there's a doubling of number of graduates, and it's a considerable surge in interest in STEM fields, meaning science, technology, engineering, math, which I think is what ended up giving the United States its competitive edge a generation later with the Silicon Valley. And you can even see that today a lot of the major internet-based startups and high-tech companies are run by people who are inspired by the space program. Jeff Bezos runs Amazon, and of course he has his own space program with Blue Origins. Elon Musk, was actually younger than the Apollo generation, but he was still inspired by Apollo and went into math, computer sciences, physics, because he was inspired by the space program. So this inspirational power of an adventure in space is not something to minimize. It's very, very important. And I think countries who today are experiencing their own space age, India, China, a few others, are doing the right thing because they are stimulating an entire generation of new people who go into these STEM fields and who will become an economic force for the country down the road. Okay. So how will we go to Mars? Well, we need a giant rocket. We're going far away for a long time, so we need to carry a lot of stuff. We need a giant rocket. So Elon, of course, is building the Starship. We'll talk about that later. But the US is building the Space Launch System, which, when it flies, will be the most powerful rocket ever flown in space. Now, here's a typical scenario. This is from my children's book, but don't let the graphics sort of deter you. It's actually based on a relatively classic scenario now that NASA is considering, among other options. But basically, you need 4 or 6 of these giant rockets that I showed you, and a 7th smaller version one of it, to put together one mission to Mars, or at least the first one. And what you do is, in step 1, you launch 4 of these giant rockets. And of course, they're not all aligned at the same time. They're phased over the course of a few years. But you launch 4 of these rockets, and they put together, as a first step, 2 robotic spaceships. That's step 2. So we have 2 spaceships that are essentially cargo ships with nobody on board. And what you're going to do is you're going to send to Mars ahead of time what you don't need to travel with. But things that you want to know will arrive on Mars in the right place and safely. Okay, so for example, the habitat that you might live in on Mars, or the rovers that you will drive on Mars. You don't need to travel with that, first of all. And second, you want to make sure that it is on Mars in the right place and has landed safely before you yourself go. You don't want to be traveling to Mars with your habitat and then realize that it's not going to land in the right place once you are yourself at Mars already. So you want to send all this stuff ahead of time, which is why we have 2 cargo ships go to Mars first. These are robotic missions. Then you have in step 3, you have 2 more giant rockets putting together your spaceship. You're still not on board. This can be done robotically or by earlier crews. And finally, when your spaceship is assembled, that's when you ride on the 7th rocket, which can be a smaller rocket just for crew. And you occupy your spaceship. This is all, of course, still in Earth orbit. And once you check out your spaceship, somebody presses the big red button and off you go to Mars. Now, what I'm showing here is a simplified sort of Mars transfer vehicle, but it has on the front end the Mars lander, and then the inflatable component there, the inflatable module, is actually an inflatable habitat, okay, or an expandable habitat, just like the one that is currently attached to the space station. These things seem to be holding up pretty well, and it's a good way to create more volume for the astronauts to sort of live in than what a rocket would otherwise allow if you were sending a rigid module. Okay, so you can increase the living space, and that's a good thing for a long duration flight. In this entire craft, the only part that comes back to the Earth at the end is the Earth return vehicle that's shown here in the middle section. That cone, that's essentially the Orion capsule. That's the one thing that would come back to the Earth in this particular scenario, that would land at the surface of the Earth, okay? Everything else would basically take you to Mars and back. And of course, the Mars lander stays on Mars because you leave Mars with a separate ascent vehicle. I'll get to that later. So this is it. This is your Starship in a less stylized version. I mean, the solar panels are a bit configured differently, but that's sort of what you just saw. And the hope is you land on Mars right next to what you have sent to Mars ahead of time, which is shown here. Okay, a basic habitat, a pressurized rover, maybe an unpressurized additional chassis for cargo. This is maybe your early infrastructure, and you want to land next to that. So hopefully you've landed very close to it, transfer to your habitat on Mars from your Mars lander. But if you haven't landed right next to it, well, then you might use the pressurized rover to go pick you up if you are within driving distance, of course, of the base. If you by misfortune land on the other side of the planet from where your assets are located, well, then you are essentially toast, and you're going to have to just, I guess, explore Mars a little bit while your spacesuit still has life support, and then eventually you will die. So how will we explore Mars once we get there? This is a very challenging terrain to explore. It's not necessarily readily drivable everywhere. So we go to places on the Earth where there are similarities with the surface of Mars. We go to Antarctica and the Arctic to find places that are cold and present a geology that is that of a polar desert, which is what Mars is. We go to the Sahara or to the Arabian Peninsula to find sand dunes that are gigantic, like the ones on Mars. We go to the Atacama to find places that are extremely dry in South America. We go to Iceland to find shield volcanoes. So all of these places are extreme in one way or another in the direction of what we might find on Mars. We go to Hawaii because it's extremely pleasant. But seriously, Hawaii is interesting because it has shield volcanoes as well. I'm going to talk to you about Devon Island, which is up in the Arctic, all right, near the North Pole. So Devon Island is, here you see it, the map on the lower left, is an island in the northern part of Canada, very near the North Pole. And it's the largest uninhabited island on Earth. And on this island, there's actually a large impact crater called Houghton Crater. The crater is 20 kilometers across, 23 million years old. Here it is, and we have our base set up on the northwestern rim of the crater. This is what the terrain looks like. And I'm not going to go into a lot of geology. I'm just going to show you a set of slides here with, on the left, Mars, and on the right, Devon Island, just to show you how many parallels and similarities we can examine and study between the two planets at this location. Okay, so we can compare Houghton Crater with craters on Mars. There's ground ice in both locations. There are rock glaciers. There are sapping valleys. There are these valley networks that are very intriguing. We actually proposed over 20 years ago that they were formed by subglacial melting. This is something that was recently reaffirmed by a more detailed study published in Nature. And here are some valley networks as well, okay, which show you how they were formed in the past on Devon Island underneath ice covers. Okay, and so this is what is making now is making us think that some of these valley networks that we see on Mars today, these dry riverbeds, might have actually formed underneath ancient ice covers on Mars, not under open air by normal rivers, but underneath glaciers. There are also similarities between canyons on Mars and Devon. So here's one of these canyons on Devon Island. Really magnificent. You can imagine training for Mars exploration here, learning how to explore the canyons of Mars. And then, of course, there are the gullies of type 1, gullies of type 2, gullies of type 3. Okay. So one of the, just to make a parentheses here, one of the biggest lesson we've learned about Mars from our studies of Devon Island over the years is that we don't think Mars's climate was ever really wet or warm as commonly suggested. We think that Mars has always been cold and dry climatically, but what was wet and warm in its past was the ground. The ground was warm in Mars, on early Mars, because volcanism was more active, because the planet was younger, and because impacts were more frequent. And because of that, the surface was warmer, which allowed ice covers to melt. But the climate itself has always been cold. And I think this is going to come as good news to most people who try to model the climate of Mars in its past as being warm, because that's very difficult. So this is an example of how valleys can form underneath ice covers. Of course, the ice cover now is sort of dying and breached in this location, but you can see how when the ice cover was still there, there are tunnels that were formed underneath the ice sheet, carving out these valleys underneath, okay? So this allows liquid water to flow even when the atmospheric pressure is very low and the temperatures are very low in the atmosphere, okay? Because the ground is warm, you are able to allow these valleys to form. There's a person right there in the middle for scale, if you can see that little person there, okay? So there's also life on Devon Island, but it's hiding in this very cold, dry desert. It's hiding inside rocks, and so this is giving us insights into how we might look for life on Mars today even. We have a permanent base set up on Devon Island. This is what it is, the Houghton Mars Project Research Station. And it's teaching us how we might operate a base on the moon in the future, but also on Mars. And we have not occupied our base in the winter yet, but this is something that we might be doing in the years to come in order to help some of the crews, astronaut crews, international crews, we hope, prepare for long journeys to the moon and Mars. Now, one of the features we have at our camp is a greenhouse where we have done experiments with, these were experiments led by the Canadian Space Agency and the University of Guelph to grow plants autonomously. So these were essentially, this is essentially a first robotic greenhouse that grew plants while we were not even there. And by the time we arrived for the summer, we were able to harvest lettuce and other plants like this, okay? But the key thing to note here is that we're growing plants without soil, okay? We just have to have nutrients and liquid water to grow plants. Just like on the right, I'm showing how you can grow potatoes. This is potatoes being grown in Vietnam without soil, just support for the roots. And then the support, these strings essentially are root systems that are fed water with nutrients, and you can grow potatoes without dealing with the soil. This allows me to go back to The Martian, the book and the movie, where the astronaut could have grown potatoes without exposing himself to the perchlorates and the toxic dirt in the Martian soil by simply providing nutrients and water to grow potatoes. And the nutrients, he had them since he had feces in bags from other crew members and himself to grow. So he could have grown potatoes with just his feces and water. So on Devon Island, we're learning how to explore, and that is an amazing thing to be doing. I love going there every summer. In fact, I live in California. I moved to California 25 years ago. I have yet to spend a summer at the beach in California. I do not know what it is to be at the beach in California in summer. I am every summer of my life on Devon Island in this Mars-like place, and I'm quite happy about that anyway. So we take robots there to test them sometimes in this terrain. But one of the things we're working on is the spacesuit. And this is something we're doing with the leading spacesuit manufacturer today, Collins Aerospace. They have a long history of, the company had different names over the course of its history. It was Hamilton Sundstrand at some point, but it has been working on spacesuits and in particular life support systems for spacesuits since the Apollo era. And what I'm showing you here is sort of the state of the art of the spacesuit. It's the best spacesuit we have. At least one of the best, and it's called the EMU, the Extravehicular Activity Mobility Unit, EVA Mobility Unit, EMU. Now, the EMU weighs 135 kilos on Earth. Yes, 135 kilos. Of course, in low Earth orbit, where it's used on the station and before on the shuttle, it weighed nothing. It had the inertia, of course, of a 135 kilo suit, but it weighs nothing. If you take the suit to the moon, it would have a felt weight of 23 kilos, okay, 17% of 135. That's manageable. You can walk around with that. Although this is not really a walking suit. You notice that there are no joints at the knees or at the ankles to really allow you to walk. Okay, you just dangle your feet here. But the Apollo suit had walking joints. And so this suit could work on the moon, potentially, weight-wise. But if you take this suit to Mars, where gravity is 38% of what it is on the Earth, the felt weight of the suit would still be 51 kilos. So that is way too heavy for you to do field work. Our goal is to somehow bring the mass, the actual mass of the spacesuit down to about 56 kilos. Okay, on Earth, so that by the time you take it to the moon, it's a trivial 10 kilos. And by the time you use it on Mars, it has a felt weight of only 25 kilos. Okay, so that's a huge challenge. We have to cut the mass of the current spacesuit, which is already very lean and mean. We have to cut the mass of the current spacesuit in half, okay, to have an effective suit for Mars. All of you who are in aerospace engineering, I would encourage you to go into spacesuit design, okay, in general. It's a very exciting thing. You should bear in mind that spacesuits are not just clothing. Of course, they are actually wearable spacecraft. Mars will belong to the people who have the lightest spacesuit. Okay, the best spacesuit let me repeat this, Mars will belong to the people who have the lightest spacesuit. Okay, so it will be an amazing thing it's a sort of a global challenge here to sort of create the best spacesuit we can for Mars, which has to be about half the weight of the current spacesuit. So Mars suits, we've been working on this for over 2 decades now. It's a big challenge to reduce the mass. And not only that, but you want the spacesuit to do more things than a normal spacesuit these days can do, such as, for example, allowing you to rappel down canyon walls if needed. Mars has this gigantic canyon system called Valles Marineris, which compared to the US here would span from the East Coast to the West Coast and even beyond. Okay, so this is not necessarily fantasy. I mean, it is right now, but we would really like to do this because we want to find fossils and signs of life on Mars, and we have to go to where the information is. Okay, so on top of that, you want a suit that can withstand dust, the Martian dust storms. This is an example of a dust storm on Mars in progress. This is a painting of a dust storm coming at you. Okay, so here I am, for example, testing some, evaluating the impact of dust that's similar to a simulant of a Martian dust that's being blown and impacting spacesuit fabric and spacesuit material. So the electron scanning microscope image here shows you how a dust grain can actually damage the fabric of Apollo type spacesuit fabric. Okay, and so we therefore should not just think that because the atmospheric pressure on Mars is so low and the dynamic pressure of wind is low, that dust is not going to be damaging to your suit. Your dust could still be traveling very fast, even with low dynamic pressure from the winds, and could damage your spacesuit material over time. Okay, so this is what we think the spacesuit for Mars in the future might look like. It's blue in color because blue is the complementary color to orange. It allows you to be more visible on Mars. You know, you want thick boots to allow you to walk on sand and rocks. Gaiters, which are these protective sleeves that you can zip on and off to protect your lower legs from abrasion and punctures. You want a hard upper torso because it's going to be more robust over time against erosion and wear and tear. Of course, the legs should still be flexible, the arms are flexible, but you have a hard upper torso. And that is actually a hard upper torso that would mate with your habitat and your rovers backwards. This is a rear entry suit. So you open the backpack, you enter the suit from the back, through the backpack. The backpack swings open like a refrigerator door. You climb in legs first. Your legs go all the way down, your feet go all the way down to the boots, and then you insert your arms, and then you close the backpack behind you, and then off you walk off. Okay, so you're now sealed inside your shell. Now, combined with the spacesuit, we have to rethink how we're going to move around on the moon and Mars. This is the lunar rover, which was used on Apollo 15, 16, 17. It was electric, built by not GM, but by Boeing. And it was very convenient, but of course intended to be limited in what it could allow you to do. It did not have a lot of range. It was supposed to keep you not too far from your lander, of course, for safety. 2 astronauts had to be carried at a time so this was one way to keep the astronauts sort of together, as opposed to giving them each their own ATV or rover. And of course, it was a mass-saving solution just to have one of these per mission. But for Mars, we really want to be able to expand our exploration, have more flexibility operationally. So we've been recommending that each astronaut have his or her own ATV, all-terrain vehicle, which is a small personal rover, basically. So we've been using this type of approach to explore in the Arctic. And what you have to think of now is your exploration unit is not just one astronaut in a spacesuit, but your astronaut in a spacesuit and his or her ATV. That's the exploration unit. And this is a self-driving ATV. It will follow you when you step off of the ATV to go pick up a rock or walk around. And what this ATV is fundamentally is a mobile portable life support system. In other words, one way to make your spacesuit lighter, which is your big challenge, is to actually offload some of the heavier elements of your spacesuit backpack onto this ATV. So for example, your ATV will carry more reserves of oxygen and large batteries. so that now your spacesuit backpack can carry just a very small oxygen tank and a very small battery. It will, of course, limit your range from the ATV, but the ATV will follow you. And so you will always be able to just jump back on and recharge. You can recharge your backpack and your batteries from oxygen and power and electrical power while driving. And then once you get to a location that's of interest, you can step off of your ATV and walk around, and your ATV will follow you. So this is a way to make your spacesuit lighter. Okay, again, by offloading heavy stuff onto your ATV. So this is something that we've come up with at the Health on Mars project as a solution to helping make the spacesuit of the future for Mars. Agency, well, you're still never alone. You have another companion astronaut who also has his or her own ATV. And if one of the ATV breaks down, then a single ATV can, in a contingency, carry 2 people. So the way you would do this is that you remove the case that is at the back of the ATV that has spare parts. And then the astronaut who is stranded without an ATV sits on a bench that gets exposed by removing the case. And this astronaut rides back facing backwards. Okay, so they just connect their backpack to the same life support connectors that would be shared between the 2 astronauts, and then they would just drive back. Okay, so that's the concept of operation using ATVs, which we're very excited about, and are hoping that this will be adopted by our current moon missions, but also Mars in the future. So here I am testing a concept spacesuit from Collins Aerospace, riding an ATV, and this is my dog, King Kong, happy to see me after a test drive. For long road trips, you want a pressurized rover, of course. So this is now a motorhome. You are inside in shirt sleeves. You are putting on a spacesuit only to go outside for EVAs, but otherwise you are inside this thing in the spacesuit. You live, work, sleep, eat, drink, drive inside in shirt sleeves in the comfort of a pressurized rover. And you even can collect samples with robotic arms there in the front by putting your head through the helmet bubble there to look at the ground. So you can collect samples without having to go on EVA all the time. Okay. So I was privileged to be the first scientist pilot actually to test drive this contraption that NASA has tested at several occasions, mostly in Arizona and also in Texas, called a Space Exploration Vehicle. At the time, it had different names. At the time I tested, it was called the Lunar Exploration Rover. Anyway, this is a very smart concept. It's a pressurized cabin that is removable from the chassis on which it sits. The chassis can be used for cargo transport, for unpressurized exploration as well, or it can be a carrier of this pressurized cabin. So the wheels can turn independently, so they can configure themselves into a circle, for example. You don't even make a U-turn. You literally turn on the spot, on the dime, which is a big advantage if you're exploring a canyon or a tight valley and you want to essentially go back and backtrack. You don't need a lot of room to make a U-turn. You can just turn on the dime and exit. Okay, so it's a very capable vehicle. Of course, it's all electric, and I think it has more windows there than it needs in the future. We could have a lot of these things replaced by displays and cameras, but of course we'll have some windows, but they can be smaller. So it's easy to drive. If you are familiar with joysticks and you're right-handed, you sit on the right. If you're left-handed, you sit on the left. You push to go forward, you pull to go backwards, you twist to turn on the dime, etc. This is when all these hours of video gaming might actually pay off. Okay, so it's very intuitive to drive, and of course you have touch screen interfaces. Now I want to not to be too rough on the movie The Martian, but this is exactly how you do not want to design a pressurized rover. First of all, it's a very angular design. A pressurized rover, remember, it's a pressure vessel, so you want to avoid angular corners. You want it to be as rounded as possible. But second, notice how this astronaut has to exit every time the astronaut exits the main cabin. The entire volume of air, of breathable air in the oxygen, in this case, okay, is from the whole cabin is lost to Mars, right? You open the door like that, and now all the oxygen that's inside your cabin rushes out. So that's very wasteful. The third thing is when the astronaut comes back from a spacewalk, he or she will bring in a huge amount of dust that's coating the spacesuit. And as you know, the dust is toxic. You want to stay away from that. It's going to end up coating everything inside your cabin and in your lungs, actually. So for all these reasons, you don't want to be doing your EVAs out of a pressurized rover that looks like this. Instead, this is how you want to design your pressurized rover. It's a rounded cabin for, of course, a pressure vessel. And we have these suit ports at the back. So these suit ports allow you, remember, you enter your spacesuit from the backpack by going directly into your suit by opening the backpack. So now these backpacks are opening into the interior of the rover, okay? So first of all, every time you go on EVA, you are no longer losing the oxygen contained in the entire pressure vessel of your rover. Okay, there is no loss of oxygen actually in this approach. Second, you keep the dust that is coating your spacesuit outside at all times. Okay, you never bring the spacesuit into the habitable volume. You just keep it outside. The third advantage, of course, is that this is actually a quick way to go out on EVAs and come back. So there is rapidity, cleanliness from dust, and economy by saving oxygen. Those are three key advantages of this spacesuit port approach. So this is how astronaut Rex Walheim, who did the last EVA on the last shuttle mission, is demonstrating how you can enter the spacesuit from the inside of the rover here. There's, of course, a double door. The door that's closest to him is the back of the backpack that will stay with the spacesuit as he walks off on a spacewalk. And then the other door that's on the far left that is sort of hosting the backpack door is a door that stays with the rover to seal the hole, of course, once the spacesuit is gone. Now, the concept as well is to explore a place, do your work during the day at an interesting place, and then you climb back into your rover, you send messages back home, you report your discoveries, you cook dinner, you go to bed. And while you're sleeping, your rover autonomously or maybe driven by mission control moves you to the next site to explore, sort of like an overnight train. I'm sure you're familiar with that in India. You ride a bus or a night train, and then the next morning you are where you need to be. So this is sort of the concept. You can drive at night, and of course, the next morning you are fresh and ready to explore a canyon or new location. So we've been experimenting with simulators, if you will, of this pressurized rover exploration approach with Humvees on Devon Island. Because we only had one at first and it was often getting stuck, this is actually a Mars exploration rover getting stuck on Mars. We think that we absolutely need two pressurized rovers to be safe, to have a safe approach to exploring on Mars and on the moon, of course, with pressurized rovers. So we brought a second Humvee to Devon Island. I just want to point out that getting any one of these vehicles to Devon Island where there's no runway, so you can't just fly a vehicle in, you have to drive it there. We drove it in the winter on sea ice. For the journey of this yellow rover, we had an epic expedition by driving the Northwest Passage on sea ice in the winter. And in case you don't have anything better to do, there's a movie that was made out of this expedition, a documentary called Passage to Mars, which, like I said, you might enjoy if you're interested in this. Okay. When will we go to Mars? And I'm speeding up here to wrap up, hopefully in time. When will we go to Mars? Well, Perseverance is on its way to Mars. This is Curiosity. We're going to continue to operate the space station at least until 2024 and probably beyond. Meanwhile, everybody is gearing up to doing more work on the moon, including sending people back to the moon. NASA plans to send the next man and first woman to the moon by 2024 or so, and the target location will be around or near the south pole of the moon. Okay. And we really have to go to the moon first because, you know, the Apollo experience now is fading. It's 50 years ago that we did Apollo. This is President Kennedy announcing Apollo, how Apollo would be done. I believe this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to the Earth. So this is the speech he gave to the United States Congress on May 25th, 1961, which is barely 3 weeks after Alan Shepard's first flight. So at the time that Kennedy committed the United States to going to the moon by the end of the decade, the entire experience the United States had in human spaceflight was a 15-minute suborbital flight by astronaut Alan Shepard, and that was it. So it was a really bold gamble to commit the nation to such an ambitious goal at the time. And of course, it was met, spectacularly within the decade in 1969. So here we have Buzz Aldrin, the second man on the moon, joining Neil Armstrong, who took the picture at the Apollo 11 site. These are the places where we landed on the moon, which were all near the equator, more or less, at low latitudes. Okay, but there's a lot more to explore on the moon, and it's, to our naked eye, it might be this relatively grayish and dull place. To people who actually are interested in geology of the moon, it's a very rich place to explore. And this is sort of a multispectral pop art style image of the moon, showing the diversity of its terrains. Okay, so there's a lot to explore there. Where we plan to go is the south polar region of the moon, where there are craters that are deep enough and pits where sunlight never shines. And these places are therefore extremely cold. They can cold trap water ice. And as you know, water ice is a resource, so there's a strategic advantage to being able to understand how much water ice there is and be able to access it for future exploration. Shackleton crater, actually, which is at the very south pole of the moon, is 20 kilometers in size, very comparable to Houghton crater. And we think that astronauts going to Shackleton crater or its vicinity should come to Houghton crater on Devon Island for their training, because they will have a similar scale of exploration to carry out and a lot of similar geologic features. This is what the terrain looks like and how it compares to the moon at Houghton crater on Devon Island. Apollo 17 on the left, Devon Island on the right. There are also caves on the moon, which I'm interested in. The ones that are, these are candidate caves near the north pole of the moon, about 500 kilometers from the north pole of the moon. These are very intriguing because these caves might be cold enough to cold trap water ice as well. There are many caves known at lower latitudes that are going to be too hot, too warm to have a good chance of harboring ice in them. But these caves that are near the north pole of the moon are very intriguing, and we've been finding many more this summer with students. So one way to explore these caves is using the Globetrotter mission approach, which is essentially a hopper protected by airbags. Okay, and so I'll just skip through this, but this essentially will allow us to explore caves on Mars, which, as you know, have the potential of harboring life, since these would be sheltered environments associated with volcanoes, which might still be active and therefore warm. So warm and moist. So exploring caves on Mars is a very exciting prospect, and we should start doing that on the moon as practice. Of course, in the near future, for Mars, we will have the Perseverance's deployment of the first robotic aircraft on any planet. In this case, a robotic helicopter designed by JPL, designed and developed by JPL. On Mars, it's a magnificent flying machine. Because the air is so thin on Mars, these rotors have to spin about 5 times faster than rotors on the Earth. So the RPMs of each one of these counter-rotating rotors here is going to be 2,400 RPMs, okay, which is sort of mind-boggling. But keep your fingers away from the rotors. Okay, and we ourselves think that drones have a great future on Mars and possibly even on the moon, not with rotor drone on the moon, but thruster drones. But on Mars, we could use rotor drones, and we've been working with this company in Norway called Intention, and Collins Aerospace, the spacesuit developer, the spacesuit life support system, and informatics developer, Collins Aerospace in the US, in creating the astronaut smart glove. I won't go into details on that, but if you're curious, you should go to YouTube, and you will be able to just search for astronaut smart glove and watch the 7-minute video that demonstrates what this is. So in terms of going to Mars with people, we might go to Mars orbit first and not bother with landing for the very earliest missions. At least that's what I would recommend for NASA. So we could explore the moons of Mars first. This is on the far left, the famous picture taken by Bill Anders from Apollo 8, looking at the Earth from the moon. Okay, and at the same scale, this is what Mars would look like from its outer moon, Deimos, and how big. So Deimos and Phobos are much closer in a relative sense than the moon of the Earth is to the Earth, and therefore we would have a spectacular view of Mars from any one of these moons, which is, I think, a exciting prospect for humans exploring these places. This is a painting of astronauts exploring Deimos, a painting of astronauts exploring Phobos. Okay, they would use MMUs, or the new generation of manned maneuvering units, and these jet packs to fly around these low gravity worlds. Gravity is so low on Phobos, for example, that on the left here, I'm showing you John Young famously jumping off the surface of the moon on Apollo 16. He was able to jump with just one strong push on his legs, 0.47 meters off the ground. If with the same push on his or her legs, an astronaut on Phobos, shown on the right, could rise all the way to 134 meters, okay, with that same push, because gravity is on Phobos is 1,600 times less than what it is on the Earth. So it would be a 7-minute round trip hop, okay, 3.5 minutes to rise to 134 meters, and then you would slowly fall back down. It's another 3.5 minutes to reach back to the surface. So it's an amazing dynamic world. Well, an amazing world for sort of astrodynamics of this kind, low gravity. And the Statue of Liberty, just to be clear, is not on Phobos. It's in New York, but it's just shown here for scale. And then, of course, by the 2040s, Phobos and Deimos could be explored in the 2030s. By the early 2040s, if not the late 2030s, we should have humans on Mars with the first embryonic infrastructure. Now, SpaceX, of course, is a wild card. Elon is developing the Starship. This might beat the calendar significantly, and we could have humans on Mars, according to Elon, maybe by the end of the 2020s, which, of course, I have no complaints about. The sooner and the more the merrier. Ultimately, I think we want to cut the travel time to Mars by nuclear thermal propulsion, which could cut the travel time to about 3 to 4 months instead of the 6 to 9 months. That would be a good way of making going to Mars easier. And one of the greatest developments recently about sending humans to Mars is NASA convening the first workshop ever to start considering landing sites for humans on Mars. This to me happened, happened in October of 2015. This to me was sort of the most important development in NASA's commitment to sending people to Mars in recent years, which is the explicit convening of this workshop to propose landing sites. I mean, NASA's been working on sending humans to Mars for a long, long time, of course, but this to me was a very momentous event because it sort of made it very real all of a sudden to start thinking where humans would go. So About 47 sites were proposed, some exciting, some less, but of course exciting to everyone who proposed their site. I actually led a team that proposed the Noctis landing site, which is on the left side of your map here, very near the volcanoes, but also on the western end of Valles Marineris. And the whole idea of being there is that you could go search for extant life, in other words, life that's still possibly alive today, by going to the warm and wet volcanoes, if they're still active, to the west, and by exploring ancient life and looking for fossils, by exploring the canyon and the canyon walls to the east. So it's sort of a strategic location scientifically to occupy on Mars, Noctis landing. So here we are at the Noctis landing site, and I just want to show you where it's located. This map has some grayed out areas. We were given some constraints in proposing the sites. You cannot go beyond 50 north or 50 south because it's too cold for the electronics, too difficult to power things. The winters are too long, too many months of darkness. So you want to be at lower latitudes. And also you cannot be too high in elevation. So all the areas that are grayed out, including Olympus Mons and much of the volcanic region, is gray here because they are off limits. You are too high in elevation to land with standard approaches. So the reason why Noctis is so intriguing here is illustrated by the fact that it's actually at a permissible altitude. It's not very high, but high enough that it gives you direct access to the heart of the volcanic region of Tharsis, and at the same time access to this canyon system to the east. Okay, so you can see what a special place it is by considering its location here. I actually have been working with a former student at the Indian Institute of Technology at Kharagpur. His name is Surab Shubham, but Surab now has graduated with his master's, his master's in geosciences, and he has been working on infrared analysis of data from Mars Reconnaissance Orbiter, and in particular helping us identify minerals in the Noctis landing region. So I'm happy to sort of report that there's actually active collaboration going on with an Indian researcher here that we have to sort of understand this potential site for human landings better and explore it in the future. So this is it. We might start with a small base and eventually it could grow to a community. I personally am not a big proponent of settling and colonizing Mars, let alone terraforming. I personally am excited by exploring this place. I think we're going to, for a very long time, have a Mars that looks like Antarctica, in the sense that there might be research stations or a single one that's contributed to by several nations, and sort of explore the place and at the same time protect it as well as we would Antarctica. Mars really fundamentally is a godforsaken place. It's a lethal environment, and there's no prospect to really make it very pleasant, except under a dome in a very localized place, in the near future, and even in the far future. So that's a longer discussion, but I just wanted to point out that as much as I'm pushing for humans to go to Mars, I'm not leading the charge when it comes to colonizing Mars. I am trying to lead the charge in terms of exploring Mars scientifically and getting an international base set up on Mars for exploration. I also think that tourism has a place to play. I think people go to Mars to visit for short term, put on Mars spacesuits, drive to the edge of canyons, visit the place for sure. But that's very different from, raising children and having sort of a real big colony there. Okay, so who will go to Mars in the end? Who will this person be? Thank you for still being there. This is close to the end. Who will this person be? So we think that for early missions, the crew size is 5 to 8 people. And that's, of course, in the scenario that I described. If Elon sends the Starship, that changes the approach. But for now, we're talking about early crews of, actually possibly 4 to 8 people. And what about the crew selection criteria? Should we have a gender mix? Okay, male, female, others. Should we have an ethnic mix, people from different ethnic backgrounds? Should we have an international mix, people from different countries? Should we have a marital mix? In other words, husband or spouse, married couples, okay, spouses traveling together. And you can imagine how that could go very well in some cases and how that could be a catastrophic idea in others. Let me just say that if you have a crew of 7, you might have, 3 married couples and then a seventh person. So just think about that, and that could give you a sense of whether or not having marital mixes is a good idea. But in any case, none of these criteria, in my view, are fundamental. They are part of our choices. They are, we might want to have a gender mix because it's a good thing. It's more representative of humanity. We might want to have an ethnic mix because it's going to be more representative of humanity. We want to have an international mix because it's going to be more representative of humanity. It's humanity going to Mars as far as I imagine it and see it, not any single nation. And so the more representative the crew is of planet Earth, the better. Okay, but those are not necessarily solutions to make the crew work better. It just makes it more representative of us. To make the crew really work well, you want Renaissance people, people who have many skills and are very capable. You want seasoned astronauts, people with experience. And you want redundancy. In other words, some skills have to be covered by more than just one person. You want, for example, more than one person who really knows how to fly, your Mars ship. Seasoned astronauts is actually a very important thing. In most science fiction books and movies, crews are depicted as made up of young people. I do not believe that a mission to Mars will have a lot of young people. In a crew of 7 people, say, you might have one person who's in their 30s, but all others would be in their 40s, 50s, if not early 60s. Part of the reason is because you want people with many skills who are experts at several things. And to acquire expertise in several things, you really need to have many years spent working on those things. There's something called the 10,000-hour rule, which represents about 7 years of focus on acquiring a particular skill. And you cannot find that in young people. No matter how smart they are, they just don't have the experience. And so we're going to end up with crews that look quite a bit older than we normally think of a crew going to Mars. Although I think that's the right solution, to have seasoned astronauts go. Also, when you're older, you tend to have had your children already, and if you're going to have any problem with radiation, and your future offspring, then you're better off by being older and having in life. Also, when you're older, your cells divide more slowly. Cancers in older people are more sluggish than cancers in young people. Therefore, there are other advantages as well to send people who are older as astronauts to Mars on a long radiation-exposed mission than young people. Okay, so finally, the qualities that each crew member should have is, of course, knowledge. I mean, you can be very difficult to get along, but if you know how to fly this ship really well and you're the best at it, well, you might still get your spot on this mission. So knowledge is really very important. Expertise, experience, skills. Second, of course, is health. You want physical health and mental health. The third thing is motivation. You have to be very dedicated to the mission success. You have to be very motivated to hope to go to Mars, because it implies that you're going to train for this for decades, to follow that dream, to achieve it, possibly to go to Mars, and you're never even sure to be selected to go. And so it really is going to require motivation to go through the whole process of getting ready for a mission to Mars. Number 4, you really have to be adaptable. You have to be tolerant to others, tolerant to change. The schedule might change, the plan might change. I do quite a bit of Arctic field work, and often people say, well, they find it more difficult than they had expected. And they might tell me, well, I didn't sign up for this. Yes, you did. You just didn't know. Okay, you signed up for it. You have to be adaptable. The plan can change. It will change. Your mission even if it goes well, will not necessarily be what was on paper when you first left the Earth. You have to be an adaptable person. That's the secret to really being successful in any expedition, in any endeavor. Okay. And then finally, you have to be altruistic. It's not about you personally. You are part of a team. Each team member is going to become family for you. You have to take care of each other. And of course, you're representing humanity. On any mission to Mars, you are representing humanity. So you have to behave in a way that is unselfish. You have to be very altruistic, okay? Gandhi-esque, if I may say so. So there you have it. I think this is my final slide. This is to stress the importance of redundancy, okay? This is a picture of a Soviet medical doctor who went to Antarctica in 1961. He turned out to be the only doctor on the crew, and he all of a sudden had to have an appendectomy. Okay, he had an appendicitis, and so he needed to perform an appendectomy. He was the only medical officer, so he did it on himself, presumably with some vodka. But the only assistant that he could count on was the only other person who sort of had some science training with him, who was the meteorologist. It is, if you want to ensure crew survival, you want to have some cross training among your crew members, and have people who can step in if one person needs the kind of help that they have the expertise in. So thankfully, Leonid Rogozov is still alive, as far as I can tell, and he came back alive from Antarctica and has a good story to tell. But this is, in my view, of sort of a perfect illustration of why you want cross training and crew redundancy on a crew to Mars. Okay, that's it. This is the end of my talk, and I'm sorry it took so long, but hopefully you're still there.
So, thank you very much, Pascal, for a wonderful presentation. We would definitely have loved to learn more and more, but time is the constraint. We have already overshoot by about 45 minutes, but it was interesting. So it was not a problem at all. So thank you very much for sparing your most valuable and busy time for making a presentation for our Nashik India chapter's World Space Week program. Thank you very, very, very much.
Thank you. If there are questions, I welcome them. You can
I
write
don't
to me.
think there is any time for questions.
No, I just wanted to leave my email. So if you want to email
I will
me
send you the questions and get the answers from you.
Okay, good. That works. That
Yeah.
works. Thank you. Thank you, Dr. Shirode. Thank you. All right. Hey, sorry it took so long. I'm really sorry.
Now,
I didn't look at the clock.
I'll be making an announcement for tomorrow's program. Our tomorrow's speaker is a very eminent speaker, Al Globus, who is a former software engineer at NASA Ames, and is also a director of National Space Society. And his subject of presentation is Space Settlement, Equatorial Low Earth Orbit. So friends, I request you to join Zoom as well as YouTube, Nashik India chapter channel, to learn more and more about the space settlement. Thank you very much for your presence here, and let us say good night in India and good day in USA. Thank you and bye-bye.
Thank you. Bye-bye.
Bye-bye.